Hello, this is Sina Parvarsh in Dr. Koda's ENGI 1331 class. Our topic is providing access to clean water in third world countries. There are processes such as desalination, but they require lots of energy and high startup costs. Another promising filtration method is using carbon nanotubes shown right over here in this figure. Now these nanotubes have their starting end polarized so that only water can flow through them. However, you have to find the right length for these nanotubes because if you increase the diameter, you're going to have unwanted ions flowing through these, and if you make the diameter too small, the flow rate of the water is going to be decreased, making it inefficient. So let's take a look at this data here. And so this is the data that was given to us. There are 26 total timestamps. Each timestamp has 300 water molecules, and each water molecule has its own given x coordinate, y coordinate, x velocity, and nanometers per picoseconds, and y velocity and nanometers per picoseconds at C, D, E, and F respectively. It also gives us the y high and x high shown over here. So let's go ahead and take a look at our actual code now. And so this is basically the way we extracted the data. We use the command xlsread, our title of the Excel, and then what it wants to extract. So we extract all the data from D2 all the way to D301, and we did that for the y position, x velocity, x position, and y velocity. Do that for all 26 timestamps. So let's go ahead and take a look at our second section here. And then we just have all the 26 timestamps for the y position, x velocity here. And so first thing we did is we added a user input. So when we run this section, it's going to ask the user, please input the height of the desired nanochannel in nanometers. So it's going to enter that, and it can't be less than 0 and it can't be equal to 0 for obvious reasons. You can't have a negative diameter, and you can't have a diameter that's equal to 0, otherwise you don't have anything. And so over here are some of our calculations. This is just the given length here that was in our Excel. And this YP right over here is going to be multiplied by Y high. Our Y high was the user input, if you remember correctly. And our YP is the fractional data that was also in our Excel. And we set this equal to YP underscore H. Now over here is we create a laminar flow using the quadratic function. So we use polyfit. Make that polyfit, calculate the YPH, the XV, and we use 2 because it's a quadratic function. Set each one equal to A, B, and C respectively. And then this S per F is, just the equation for the laminar flow. Right over here is just the range of the pipe diameter all the way up to the user input and increments of 0.01. We set our U, which is our actual equation code. And right here is a little unique. What we did was we used the vertice of our laminar flow, and that vertice is going to give us the maximum velocity at a certain point. And we display using S per F here. So going to our first figure. Our first figure is going to be the laminar flow, and we use subplot because we're going to have 3 different figures. And we use 3 to 4 here because we want our laminar flow picture to be huge. We want it to be the biggest one because it's our most important. So what we do is we obviously just set the plot, just your basic plotting functions, and this is the plot for the vertex, this is the plot for the actual flow rate line, and then you have your X label, Y label, title, etc. And what we did uniquely here is something that we actually weren't taught in class. So what we did was we take the legend, set it equal to HL, and then we use the function set to make this HL font size slightly bigger, just a little something extra we threw in. And so for our second figure here is a scatter plot using subplot once again, but we only use 4 timestamps shown over here. And the reason for that is we have 300 water molecules per timestamp. So for obvious reasons, if you put too many water molecules in a scatter plot, you're just not going to show a pretty, you're going to be confused, you can't read the graph properly. So we limited it to 4 timestamps, still gives an accurate display of our water molecules. And going down to our third figure here, and this is something we did differently, something we weren't taught in class once again, and it's actually our quiver plot. So what a quiver plot is going to have the x and y position of our water molecules, but the unique part is it's going to be showing the direction of the velocity. And so what we did was we only used timestamp 1 because 300 water molecules is going to be taking up a lot of space. But what we also did differently is we used the screen size for our subplotting. So it's going to be set to where it takes up the entire screen, or at least close to it, as soon as you run the function. So we'll go ahead and do that over here. Let's run this section. It's going to give us the user input. We'll start off with a small number. We'll say 1 and run that. And right over here, you see how it pops up to be large. We'll go ahead and maximize that. And let's start with the laminar flow. And so this is just laminar flow right over here. Our vertex, which is the maximum velocity right here. Our equations, of course, the vertex point. And then right here is our scatter plot. You can see the relationship with these two right here. This is just the average of this basically put into a line. So you get a better idea of the velocity at a given position. Now right here is the quiver plot I was talking about earlier. Has the y position, x position, and then the direction of the velocity. Now why don't we go ahead and run this function one more time, and let's put in a larger number, let's say 1,000. Put that in there. Same thing, you can see it goes from all the way to 1,000 here. And then everything else is kept the same. We still have our legend correctly. Everything else is working out great. Now the only limitations for this is basically back in the user input, which is given with a conditional statement. And so what some of you might be wondering is, how could engineers use this? What is this good for? Basically, that takes us back to our problem statement where engineers should go ahead and use this instead of the desalination method, which is, like I stated previously, has a high startup cost. It's going to take a lot of energy. This is a lot more efficient. This is, if you find the right length, of course, and it costs a heck of a lot less. Thank you very much.